Here we're going to learn about the Debye potential. The Debye potential gives the electric potential away from some charged surface. Why is that important? Well, let's consider a couple cases. What we're considering now are ions in solution. Say we have a positive ion in solution. This positive ion will generate electric potential away from that ion, and let's use the symbol phi of R to represent the electric potential. Now that'll be a positive electric potential. What that will do will preferentially attract negative ions around it. Of course, there'll be some positive ions too, but if you sum those up, there'll be a net negative number of ions around that positive charge. What we're looking at, or what we want to do, is to calculate activity coefficients, chemical potential, and so on. And the activity of these ions around the solution, negative and positive charges, will depend upon the electric potential. This is the Debye potential. So it's important to calculate this in order to see what the activity of these ions are around the solution. Second use of Debye potential is, suppose you have a membrane, a biological membrane, and say this is positively charged. What the positive charge will do will preferentially attract negative charges in solution. These negative charges will be anions, and you have some positive charges also. But you have a counter ion. These mobile counter ions will line themselves up preferentially to the positive charge in the membrane. The potential that comes out of the charged surface of the membrane is a Debye potential. And to calculate the concentration of ions, mobile ions around that charged surface, you need to have the Debye potential. All right, so I hope I convinced you Debye potentials are useful to calculate. All right, so let's set this up. Let's first take a charged surface, right? Let's make it a sphere, and let's make this radius of the sphere A. And let's actually calculate the potential away at some distance r. This is a vector r, so in 3 dimensions, someplace away from that charged sphere. And out here, you would have some sort of charge density, and the charge density will be given by the ions in solution. Since we're chemists, the charge density will then be the ions. Well, the solution, or the equation that describes this situation, has been well known for at least 150 years. That's a Poisson equation. The Poisson equation, I'll explain what these symbols are in just a minute. This is called del, D-E-L. It's the upside down capital Greek letter delta. And del, or del squared, means take the second derivative with respect to spatial coordinates. In a Cartesian coordinate system, del squared, the second derivative, will be the second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z. Okay, so that's what del is. Rho is the charge density, how many charges you have per unit volume. Epsilon is called the dielectric constant. And this symbol here, epsilon naught, is called the permittivity, or electric permittivity of a vacuum. Epsilon naught essentially tells or governs how the potential drops off. If you have very high dielectric constant, the potential is screened and will drop off more quickly from the charged surface if you compared to when you don't have high dielectric constant. And this will depend upon the solvent, dielectric constant. The permittivity of a vacuum does not depend upon, it's just a constant of nature, it doesn't depend upon the nature of the solvent. All right, so there is the Poisson equation. And if we could solve this equation, solve this second order differential equation for phi of r, we would have what we need, how the potential varies, and then we can calculate how the ion concentration around a charged surface varies. Okay, it's a little more complicated because as the potential varies, the charge distribution will vary because we'll have mobile charges, and as the charge distribution varies, the potential will vary. So there's a back and forth. First, let's convert the charge density into concentration of ions. It's actually quite straightforward. The charge density will just be related to the concentration of a particular ion at some distance r, and to change the concentration to charge, we multiply by the signed charge times the Faraday, and then we're going to sum this up over all ions. So for example, if we have 1 molar concentration of charge, we multiply by this quantity, that will give us the concentration, the molar concentration or the charge density. Okay, so we plug that into the Poisson equation, del squared phi of r. That's 1 over epsilon, epsilon naught. The charge density now, and there's a minus sign there, is the sum over all ions of the charge in the ion times the Faraday times the concentration of that ion. And this will vary as you go away from the charged surface. So, how does one calculate the charge or the concentration of the ions away from the surface? We're going to use what's known as the Boltzmann distribution. We had one example of this already, and we'll learn more about this when we talk about statistical thermodynamics later on. So the Boltzmann distribution says the concentration of ion at some particular distance away from the surface divided by the concentration of the ion at a very far distance, as r goes to infinity, a very far distance away from the charged surface, is e to the minus the energy of that ion divided by RT. That's the Boltzmann distribution. And the energy of the ion, we know from previous, if it's in a potential from previous lecture, is the charge on the ion times the Faraday times the potential at that particular distance. So we can express the concentration of a particular ion at some distance as a concentration of that ion at some distance very far away from the charged surface times e to the minus charge Faraday potential divided by RT. All right, so there's that. We can substitute that in up here. Okay, and then we got the Poisson-Boltzmann, the Poisson-Boltzmann. So we're using the Boltzmann equation. Plug that into the Poisson equation, and we end up with the Poisson-Boltzmann equation. So, del squared phi, electric potential, is 1 over epsilon, epsilon naught, with a minus sign there, the sum over all ions of the charge on the ion times the Faraday times the concentration. Let me just use I comma infinity of for the concentration of the ion far away from the charged surface, e to the minus ZIF phi r over RT. So there's a Poisson-Boltzmann equation. It gives the potential as a function of the concentration of ions. Now this is a little difficult to solve. It's a nonlinear equation. We have the second derivative potential, but now the potential appears up here as in the exponent. What that means is that there's no analytic solution. There's no way you can write down an expression on a piece of paper for the solution to this phi of r. Instead, you have to solve the Poisson-Boltzmann equation numerically with an Excel spreadsheet or with a computer. Back in the 1920s, when the Debye and Huckel were working on their theory of ions in solution, there were no electronic computers, believe it or not, and so what they did was to expand this exponential in terms of a Taylor series and keep just the first two terms in the Taylor series. We've done this a couple times before in the course. Just let's actually do it once again here. We're going to expand this exponential here, e to the CIF 5r over RT to two terms. So it's 1 minus this 1 plus x squared over 2 and so on, but we have this minus sign there, so it comes 1 minus ZI F5R over RT. So there it is, expanded just to the first two terms. What this means is that you have small energies up here, or small potential. All right. So if that's the case, then you can just take the first two terms and you get a pretty good approximation. So if we now substitute this this expression for the exponential here, we'll have this expression for the Poisson-Boltzmann equation, where we have small potential. We'll have the sum over all the ions of the charge in the ion times the Faraday times the concentration of the ion very far away, 1 minus Z F 5R over RT. So what we've done is we linearized the Poisson-Boltzmann equation by doing this Taylor series expansion and just keeping the first two terms. So this is called the linearized Poisson-Boltzmann equation. All right. Well, let's clean this up a little bit. We can multiply this sum there and the sum there. So we'll rewrite the equation here, del squared 5r minus 1 over epsilon 0. And we're going to distribute that sum, so this will be the sum over all ions of the charge in the ion times the Faraday times the concentration of the ion far away from the surface, minus the sum over all the ions of the charge on the ion times the Faraday times the concentration of the ion infinite distance away times the charge in the ion again times the Faraday over RT times the potential R. Okay, now this is kind of cool. This is the sum of all the over all the ions at a far away distance from the surface. Far away distance, you equal chance of having a positive and negative charge. In other words, at the far away from the surface, you have electroneutrality. And since this is a signed charge, positive for cations, negative for anions, and you have just as many positive charges as negative charges, this means that this term is equal to 0 because of electroneutrality. Okay, so we can rewrite this, make it a little simpler. The minus signs will cancel out. So this will be 1 over epsilon naught, sum over all the ions of Z squared, there's a Z squared, F squared, times the concentration at infinite distance away, divided by RT times the potential 5R. All right, let's pull out of this equation all the terms that don't depend upon I, because we're summing over I, so those will be constants. We can pull them out. So let's see, the F squared will come out. The RT will come out. And the phi will come out. And here we just have the sum over all the ions of Z squared concentration at infinite distance away. This you may recognize as twice the ionic strength. In fact, let's multiply this by 2 over 2. So if we take that 1/2 and put it here, this will just be the ionic strength I. Oh, so let's replace that. So now we have the linearized Poisson-Boltzmann equation as, and let's take that 2 and put it here, and we'll take the 1/2 and use it there. So this will be equal to 2f squared times I divided by epsilon naught RT times the potential phi of R. And let's further simplify this. This is what scientists do. Let's give this a symbol kappa squared. So now we have finally del squared phi of R is Greek letter kappa squared times phi of R. Now what we're going to do is set up a particular system. Again, let's use a sphere. So we have a charged sphere, and what we're looking at is the potential away from that charged sphere. Let's use spherical coordinates. Spherical coordinates means that if you have this now spherically symmetric system, no matter what angle you look at, as long as the distance from the center or from the origin is equal, you'll have equal potential. So it's independent of the angle in the spherical coordinate system. It just depends upon the radial distance from the center of the charged sphere out to some point in space. So in general, these vectors represent 3 dimensions, but with this spherically symmetric system, we can reduce those 3 dimensions just to a single dimension. So we'll have a differential equation just with a single variable. If you remember, we had del squared was the second derivative with respect to Cartesian coordinates. If we change now to spherical coordinates, now we have to write what del squared is in spherical coordinates. Del squared is, when you make that coordinate change, 1 over r squared d by dr. Again, we don't have partial derivatives anymore. We just have a single variable of r squared d by dr. So this is the del squared operator in spherical coordinates, where we have gotten rid of the angular dependence because we have a spherically symmetric system. So this means that we can rewrite the linearized Poisson-Boltzmann equation, 1 over r squared d by dr of r squared d phi by dr. And again, now this is just a single coordinate. That's just equal to kappa squared phi of r, that single coordinate. And if we multiply by r squared, we get this as the differential equation is equal to kappa squared r squared phi of r. And there's a phi of r there. Okay, so there's a linearized Poisson-Boltzmann equation written in this term, written in this way. Now, if you look up in differential equation textbooks and so on, this has a standard solution, and I'll just write down what that solution is. You can verify it by taking the solution, plugging it back in here, and showing that you get the equation back again. This means that this solution to this again is the radial distance from the center of the sphere. That is equal to some integration constant, let's call that alpha, we'll determine alpha in just a minute, divided by kappa r e to the minus kappa r. Alright, so there is the general equation for the Debye potential. Where the constant alpha depends upon what system you're setting up, the initial conditions. All right, so let's actually do that. So let's take again our typical system. I'm going to draw it the third time here. We have a sphere of radius a, and let's say right at the potential, right at the surface, the potential there is phi 0. This means when R is equal to A, we want the potential at A. We're going to give that the symbol phi 0. So let's go ahead and put that in and solve for alpha. We're going to determine what alpha is for this particular set of conditions. So phi of A, which we're going to give the symbol phi 0, that's equal to alpha over kappa A, substituting A for R, e to the minus kappa A. Solve this for alpha. Alpha will be phi 0 kappa A e to the kappa A. Let's plug this in here. So for this system, we have that the Debye potential is equal to the constant kappa A phi 0 divided by kappa R e to the minus kappa R e to the kappa A. Note that the kappas go away, so this is just equal to phi 0 A over R e to the minus kappa R minus A. All right, so there's the Debye potential for a sphere of radius A where the potential at the surface is phi A. Debye potential. All right, so let's touch base with our PowerPoint slides here. Well, so we sort of really got ahead of ourselves. So here's a Poisson equation. We use the Boltzmann distribution to get how the ions vary, the concentration of ions vary, and finally we get the Debye potential. All right, here's a plot of the Debye potential as a function of distance away. Right here, the radius of the charged sphere is 2 nanometer, and the potential at the surface is 40 millivolts. All right, and here the concentration of ions is about 0.1 molar. So this is how the Debye potential varies away from that surface. You see, it's a fairly short-range potential for typical ion concentrations of like 0.1 molar. The potential essentially has died off to 0 after 1 nanometer away from the surface. Let's look in more detail about this kappa. 1 over kappa is the Debye length. So let's go back here and take a look here. Oh yeah, so let's actually write this as this term here as e to the minus R minus A divided by 1 over kappa. So 1 over kappa governs how fast this exponential is going to die off. Remember that kappa was equal, well, kappa squared was equal to 2f times ionic strength divided by epsilon naught RT. Sorry, that's 2f squared. So that kappa is the square root of 2f squared over epsilon naught RT. I'm writing it this way for a reason. 1/2 times the square root of ionic strength. So if you increase ionic strength, kappa will increase, but 1 over kappa will decrease. So the Debye length of the potential decreases with ionic strength. In fact, it goes as 1 over the square root. Sorry, that should be 1/2. 1 over the square root of ionic strength. So in general, you increase ionic strength, you increase shielding, so the potential from the surface will drop off more quickly, and it'll drop off as the square root of ionic strength. All right, so that's the Debye potential, and what we're going to do next is to use these concepts in order to actually finally calculate activity coefficients of ions in solution.